Good day everyone. So today's topic is estimation of heating and cooling time in a batch reactor. So in this particular topic we are going to see about the heat load calculations and how to perform energy balance efficiently. I will try to explain using case studies. Before going into that, I will try to explain these things using a simple step-by-step procedure. The steps involved in estimating the heating time as well as cooling time is: step number 1, estimate the demand from system. Step number 2, estimate the supply from utility. Step number 3, equate both demand and supply. Step number 4, estimate the required time for heating or cooling. So these are the basic steps involved. In my previous videos, I have explained you how to estimate the demand as well as the supply and the equations which are associated with these two things. Let's take a case now. Case for estimating heating duration. So the scenario is, need to estimate the time required for heating a reaction mass from 30 degrees centigrade to 80 degrees centigrade using hot water and steam. Let's say the reaction mass contains water. And equipment capacity is 5 kL with SS316 MOC. This is the scenario. Now let's begin. First of all, we have to make a note of the given things. Reactor capacity is 5 kL. The reactor capacity is 5 kL. Initial temperature is 30 degrees and final temperature is 80 degrees. Reactor MOC is SS316. So these are the given things. First thing is, we need to estimate the demand. Demand equation is mCp delta T or m lambda or a combination of mCp delta T plus m lambda. Since in this specific scenario we got only sensible heat transfer or sensible heat is being done, so we need to select the equation. Demand is nothing but mCp delta T. If it's a latent heat, we need to select m lambda. If it's a distillation, we need to select both mCp delta T plus m lambda. we have to make a note of this. First thing is M. M is nothing but mass flow rate. Or it is going to be M by T. Capital M equals to M by T. And in this scenario, the mass is going to be water. The reaction mass contains water and the reactor capacity is 5 kL. So I'll be taking 80% occupancy. So 80% occupancy out of 5 kL is 4 kL. So 4000 liter of water is available in the reactor. The density is 1 kg per liter. Specific heat of water is 1 kilocalorie per kg degree centigrade. The delta T is 80 minus 30, so it's 50. The total demand is 4000 multiplied by 1 multiplied by specific heat multiplied by 50. So we need total 2 lakh kilocalories of energy. This is the demand. Now the second thing is going to be the supply. The equation for supply is UA LMTD. Since it's a SS316 MOC reactor, the U nothing but the overall heat transfer coefficient we are going to take in the range of 250 kilocalorie per hour meter square degree centigrade. And coming to area, the heat transfer area is approx 12.75 meter square. You can calculate this heat transfer area based on the last video that we have presented you. From this total heat transfer area, we need to calculate or estimate the effective heat transfer area. Effective heat transfer area is nothing but the total heat transfer area multiplied by the occupancy. It is 80% in this case. So it is 10.2 meter square. We got U and we got A. And coming to this LMTD. In the first case, we are going to heat the water from 30 to 80 degrees using hot water which is available at 90 degrees. That means initial temperature is 30 and final temperature is 80. Coming to hot water, the initial temperature is 90 and the final temperature is around 86 degrees. Now the LMTD equals to 90 minus 30 minus 86 minus 80 divided by ln of delta T1 by delta T2. So it's around 23.45 degrees centigrade. And now the supply is UALMTD, that is 250 multiplied by 10.2 multiplied by 23.45 degrees centigrade. This is in kilocalorie per hour. That means in 1 hour we are going to supply 59,800 kilocalories of energy. So in order to calculate the time required for heating, we have to divide demand with supply. Here in this case, the demand is 2 lakh kilocalorie divided by the supply is 59,802 kilocalorie per hour. So the time required for heating the mass is 3.34 hours. It's nothing but approx 3.5 to 4 hours it will take. This is how we are going to calculate the time required for heating theoretically. And now we are going to take the same scenario, like from 80 degrees we need to cool the mass to 10 degrees. Or I think one more thing is left, that is, first of all we have tried with the hot water. Now we need to check the scenario for steam. I'll repeat the same supply. Why? Because the demand remains the same, only the supply varies. Why? Because we got steam in place of hot water. So I'll try to repeat the same formula and same thing. Overall heat transfer coefficient will remain same as 250 kilocalorie per hour meter square degree centigrade. The effective heat transfer area will remain same, 10.2 meter square. Coming to LMTD, this is going to vary. Initial temperature is going to be 30 degrees for reaction mass and finalize 80 degrees. And coming to steam, as it's in gaseous phase, we are going to utilize only the latent heat of it. So I'll be taking the temperature of steam around 110 degrees. To know the exact value of temperature, the steam temperature, we need to refer the steam tables using the pressure of the steam. As it's 110 degrees centigrade, we need to calculate the LMTD once again. So it is going to be 110 minus 30 minus 110 minus 80 divided by ln of the same thing. It is almost 51 degrees centigrade. Now the supply is the same thing, UALMTD 250 multiplied by 10.2 multiplied by 51. Now let's try to calculate the time required for heating with steam. That is demand by supply. The demand remains the same, that is 2 lakh kilocalories divided by the supply 1,29,900. Okay, so it is kilocalorie per hour. So the total time required for heating the mass is 1.5 hour. If it's hot water at 90 degrees temperature, it is going to be 3.34 hours. If it's steam at 110 degrees centigrade, the duration is 1.5 hours. This is how we need to estimate the heating durations using different utilities. Now let's try to do the case for cooling using a utility. The scenario is estimation of time required to cool the reaction mass from 80 degrees centigrade to 10 degrees centigrade using chilled brine, which is at minus 15 degrees as utility. Okay, this is the scenario. Reaction mass contains water. And the equipment MOC is SS316. Now we need to perform the same calculations again. This time we are going to cool. Now let's try to check the demand. Nothing but MCP delta T. Why? Because here there is only sensible heat transfer happening. M is 4000 liter water. Density specific heat is 1 kilocalorie per kg degree centigrade. And the delta T, or I can say the initial temperature, is 80 degrees. The final temperature is 10 degrees. The demand equals to MCP delta T, that is 4000 multiplied by specific heat multiplied by 80 minus 10. This is approx 2,80,000 kilocalorie of energy. Now let's come into supply. That is UALMTD. Overall heat transfer coefficient will remain same, approx 250. The effective heat transfer area, since it is having 80% occupancy, I am going to take the same value, that is 10.2 meter square. Now let's come to the scenario of LMTD. The initial temperature is 80 degrees, the final temperature is 10 degrees, and on the other hand I got a utility of chill brine. So initial temperature is minus 15 and the outlet temperature is, let's say, at minus 11 degrees. The LMTD is going to be 80 minus 15 minus of 10 minus 11 divided by ln of 80 minus 15 divided by 10 minus 11. It is coming around 49.03 degrees centigrade. Now the supply is the overall heat transfer coefficient multiplied by heat transfer area multiplied by the LMTD. It is around 1,25,000 kilocalorie per hour. Now the time required for cooling is nothing but the demand by supply. That means 2,80,000 divided by 1,25,000. So it is approx 2.5 hours using chill brine. If you are going to vary the utility, automatically the time will vary. And one more thing that we have to take care is the overall heat transfer coefficient. In this case, each and every time I am going to take the overall heat transfer coefficient as 250 kilocalorie per hour meter square degree centigrade. But actually the point is the overall heat transfer coefficient is going to vary based on the utility and sometimes based on the reaction mass that we are going to handle. In order to estimate the actual overall heat transfer coefficient for a specific equipment, we need to take trials. Either it can be heating trial or cooling trial based on the utility that we are going to perform, that or the utility that we are going to use for a specific operation. We need to consider the same utility for the trial also. And how to take the trial and what is the actual procedure of estimating this overall heat transfer coefficient, you will see in the upcoming videos. So thanks for watching the video. If you like our content, please do subscribe and share it with your colleagues. Thanks everyone.